Our first speaker is Dr. Justin Kermetis, who is a research assistant professor at Virginia Tech's National Security Institute, and also has a background in math. He works on development of theoretical and computational frameworks for Bayesian data analysis, including incorporating and balancing data and expert opinion into decision-making, estimating model parameters, including high or even infinite dimensional qualities from noisy data, and designing experiments to maximize the information gained. His research interests include parameter estimation, uncertainty quantification, experimental design, high-performance computing, artificial intelligence and machine learning, and reinforcement learning. Dr. Kermetis also has a background in computational science supporting high-performance computing within emergency response and disaster preparedness. So, welcome.
Thank you. Okay, so sorry, just going to adjust it so that I can see things. So today I'm going to be talking about methods for combining information from across phases of test. And I'm going to be comparing a few different ones for sort of some complex surrogate system models. So just to start, when I talk about integrated test, I've heard different people have different definitions, so I'll just define mine, maybe provide some motivation, and then describe the methods I'm going to be comparing. So really the goal here, when I talk about integrated testing, is DoD programs in particular have a lot of data associated with them that are collected throughout the acquisition lifecycle, right? So we have operational test data, right? That is sort of the closest thing we can get to from a test and evaluation perspective to an operational environment. But then before that, right, there's tests that occur during development of the system. There's, often these systems come with modeling and simulation capabilities. There might be similar historical data or subject matter expertise that we could bring to bear on these systems, right? So we want to kind of take all of this disparate data and build it into one cohesive picture about how this system is going to behave. And really the goal here is, so if we can do that, right, then we can understand the systems earlier, which might allow us to design more optimal tests later. And, this isn't just something that I made up. One of the speakers this morning talked about this guidance, or maybe it was in one of the sessions I went to. But anyway, so this is guidance released by the DoD, I think in December, that talks about test and evaluation. And in a few different places, it talks about the need to integrate multiple sources of information. It talks about Bayesian methods in particular, talks about sequential testing. And so that's really sort of where this motivation is coming from. And I should have mentioned, this is all part of work that Virginia Tech is doing that's funded by DOT&E. So they're our partner here. I meant to thank them at the beginning. Okay, so I'm going to be talking about sort of two classes of methods for combining information. One is frequentist, and there are sort of two types of frequentist models that we'll be using. One is, so we're going to define a statistical model, and then we're going to be fitting it to our data. A naive way, or maybe sort of the way you might think to do it initially, is take all of the data that I mentioned here and put it into one sort of bucket and then fit a model to all of it. Okay. And assume maybe that it's all equivalent. So we're not doing anything to kind of account for how it was collected. And then maybe a slightly more complicated model is we're going to do blocking. We're going to add factors to our data set that sort of indicate, okay, this data is from modeling in SIM, this is historical data, this is DT data, this is OT data. And we're going to allow factors to reflect the differences in between those test phases, because we know things may have changed about how the data is collected or the environment or the people that were running the test, that type of thing. And so just as a simple example, right, we might add a shift. We might say, okay, we think that performance in DT will be sort of biased relative to what we might expect to see in operations. And so we're gonna put a factor into our model that reflects that shift and then fit it to the data. Okay. Okay, so that was frequentist. I'm also going to talk about Bayesian methods. This is my one slide on Bayes. So there are three key components to Bayesian inference. One is the prior. So this reflects what we know before coming into taking any tests. So if we, if I ask you what your belief is about the parameters that we're trying to estimate, and you haven't collected any test data, this might reflect that, right? So that could be built off of the historical systems, subject matter expertise, or previous test phases, maybe. Okay. And then we're going to build in the data through something called the likelihood. Okay. And this just sort of reflects how likely we are to see the data based on, based on a given value of the prior. And then what we get out of that is proportional to the product of those two is the posterior, and this is kind of our updated understanding of the parameters. And really, I mean, one way to think about this that I think is sort of intuitive is that when humans learn, right, when we come into an experience, we have some understanding of the world going in, and then we collect, which we can think of as the prior. And then we collect data, right? We go through the experience and we learn things. And then we come out with an updated understanding that it sort of reflects an understanding that sort of matches both what we knew going in and the data that we collected, right? It might be, we didn't know much going in, it might be mostly focused on the data. If we knew a lot going in, then maybe, we would not, our updated understanding might not change that much based on the experience that we had. Okay, so how do we apply Bayes to T&E? If we were doing it on a single test phase, it might look like this. So we would come in with a prior that's based on whatever information we have, right? And then we collect test data. We run it through this Bayesian machine and we get out an updated understanding, right? Which represent point estimates of the parameters we're trying to estimate, as well as uncertainty associated with those parameters. And then if we want to iterate on that, right, let's say we get new test data, right, we can take our posterior and use it as our prior going forward, right? Because our posterior represents our new understanding of the information that we have, our new knowledge about the system. So it's natural to then use that as the prior if we get more data. Okay. One caveat there is that if the new data is collected in a different way, like if we've changed test phases, right, and we have we have more operationally realistic operators, or if we've changed test factors, or if we're testing in a different location, right, we might think that the data might have changed somewhat. And so we might want to adjust the posterior that came out of one phase before we go into the next phase. And so we might do something like downweighting it, for example. So here I'm trusting my point estimate from the previous data, but I'm adding uncertainty to allow the data that I'm collecting next to sort of move my estimates. Okay. So it's kind of that's just this distribution getting a little bit wider. Okay. And then we can just take it and we can iterate, right? So this is what I'm going to call informative priors. It's Bayesian method that I'm going to compare to. Okay. So how am I going to use this for a DoD program? So one of the things that makes DoD testing interesting is that different programs fall in different spaces in what I call this like consideration space, right? So different DoD programs might have a different cost associated with a test, right? They might have different resources that are required, the availability of those resources, the scheduling, all of those things might change to make operational tests more or less feasible to collect, right? And so what that means is that a variety of different DoD programs, right, that fall in different spaces in this might be necessary to use different methods to integrate information. Okay. So there's some decision making that needs to be made about what the right method is to interpret these different programs that fall in different spaces here. Okay. A challenge for me in academia is that DoD data can be hard to get hold of. And even if we can get access to it, right, like we do at VTNSI have classified capabilities and things like that. But even then, it's hard to engage students on. It's hard, often we want to publish, we want to disseminate results, we can't do that. So the way that we are dealing with this on this project is by trying to make synthetic data that simulates some of the real challenges associated with DoD programs that I outlined in that sort of considerations diagram. One nice thing about that, from the perspective of this talk, is that when we make synthetic data, we know what the truth is, and so we can measure how good we do at recovering the truth. And so that allows us to sort of evaluate how the methods are doing. Okay, so I'm just going to talk about how we are generating synthetic DoD-ish data. So we started with a model that was created here at IDA in this paper mentioned at the bottom of the slide here. And this is a notional model for a counterfire radar, behavior of a counterfire radar. So this is a system whose goal is to observe a shot by an adversary and to locate the origin from which that shot was fired, right? So that we can fire back at it. And so they in this paper, they sort of wrote down this model and relevant factors for this system, right? So like if we're observing a shot, the munition type might be a key factor, right? The shot that was fired. The angle, either that the shot was fired or the angle of orientation between that shot's trajectory and the radar, both might be factors. How far, this last factor, radar to weapon range, will also, of course, affect the ability of the radar to locate the target. Okay. And so we're going to take that model and we're going to use it to sort of mimic the types of data we might get for the DoD. So we're going to use that full model as our operations model. Okay. So this is sort of the approximation to real life, right? Because it's the most complicated thing. And in practice, when we test, we're going to necessarily not going to be able to fully recreate what we would see in practice, like in real life. And so we're going to make a series of simpler models that are represented below. So in operational testing, we're going to represent our operational testing model, we're going to drop the quadratic terms from the full model. And then for our DT model, we're going to make it, one step simpler. We're going to imagine that we can't test quadrant elevation as part of developmental testing. And then we're going to go one step even simpler when we go to modeling and sim, because maybe our modeling and simulation capabilities just can't reflect all of the factors associated with this counterfire radar. Okay. Okay, and then just some nerdy stuff. So we're going to take the model and we are going to use it to, like these models, we will use to represent the mean of a Rayleigh distribution, from which we will then draw to simulate point of origin error for like basically the error in how far away the estimate for the radar was from the actual target. And the reason I picked a Rayleigh distribution is that if you imagine the error in, east and north, or, X and Y are normally distributed, the norm of that 2D normal random variable will take a Rayleigh distribution. Okay. Okay, so this R code that we have can simulate a lot of different things, right? We can use it to compare analysis methods. We can also generate data sets that have different sizes, the different factors that I just showed you, different models, different test designs. If we want to look at sort of the effect of choosing different test designs for the different test phases, it has all of this stuff kind of built into it. Okay, so now I'm going to talk you through, so that's sort of the framework. Now I'm going to talk you through some numerical results that we did to kind of simulate some of the considerations that might be worthwhile to take into account when doing integrated testing for DoD programs. Okay, so I mentioned Bayesian and frequentist. I actually use 5 models. You'll see 5 models in all of these comparisons. The first 3 are frequentist. So first is just kind of a baseline. I'm going to do the traditional thing, which is do my estimates from the OT data that we generated, okay? And then I'm going to use the two integrated models that I talked about. One is with blocking, where the shift factor is added to represent the fact that DT and OT might be biased. And then one is without blocking, where we're just going to take all of the data that from these three test phases and fit a single model to them and treat them as equivalent. And then I'm going to do two types of Bayesian informative priors that I showed you, this iterated Bayesian inference. In one, I'm going to double the uncertainty of all of the parameters when I go from modeling in sim to DT and then from DT to OT. And then in one, I'm going to be slightly more aggressive. And on the intercept parameter, I'm going to just reset the uncertainty to what I came in with from the prior at each test phase. This is just saying, okay, I'm going to take the point estimate, but I'm going to be very aggressive about increasing the uncertainty again so that I can land somewhere different if my estimate was biased. Okay. So, and then the key metric here is I'm going to be comparing, because we know the truth, right? Because we are working with synthetic data, right? We know what the operational model is. I just showed it to you. And so we're going to compare how well we do at recovering the Rayleigh mean from that operational model based on these different methods of integrating the information. Okay. So all of this will be in terms of root mean squared error across a full factorial data set. So it's sort of like the closest like a real life test. Okay, so in each of these, I ran a whole bunch of different scenarios because I didn't want to just rely on one, like one set of bad draws or something like that might sort of bias the results. And so in this case, in this example, I tried to keep OT relatively small because that's where we might see benefit from integrating information. So I took like a set of different DT number of trials, a set of DT number of reps, a set of OT number of trials, a set of OT number of reps, ran all combinations of those, and then several reps for each of those combinations. So it's about 100 test cases of synthetically generated data for this example. Okay, so let's look at some results. I'm going to show a few of these scatter plots. So it's maybe worth lingering on this one for a moment just to make sure that we understand it. So in each case, I'll have a method on the x-axis and a method on the y-axis, and it'll be a scatter plot of this root mean squared error metric. And so here, for example, on the x-axis, I have the frequentist approach using only OT data. So here we're not integrating information, and we're comparing it with the frequentist method where we integrate information using blocking, right? So we have these factors to represent changes between the test phases, okay? And the simple way to think of this is the side on which the points fall is the side for which the error is larger, and therefore it's the method that's losing effectively, okay? So here, the points along the x-axis are the x values are larger, and so we are getting larger errors for the frequentist method when we're only using OT data, okay? So this is just saying that for these models, integrating information using this blocking method is almost uniformly giving us a better estimate, right? We are learning things from the previous test phases, okay? Okay, now let's look at the Bayesian methods. So here on the x-axis, I have where I double the intercept uncertainty. And on the y-axis, I reset the intercept uncertainty. So the y-axis is very aggressive down weighting when we go between test phases. And we see that maybe I was over aggressively down weighting in the y for this y method, because we're getting it's like I'm forgetting too much when I go between test phases, right? And as a result, I'm getting worse estimates for the behavior in the end, right? I guess one thing I should mention here is all of these points are colored by the number of OT data points. And so sometimes you can sort of discern trends. The trends tend to be stronger for like the yellow and maybe green points, because those are the ones that have smaller amounts of OT data, right? The method we choose is going to matter less if we have more OT data. Okay. So that's the Bayesian. And now let's compare the effect of blocking. So here on the x-axis, I have the blocking where I add the factors by test phase. And on the y-axis, I have when I don't add the factors, right? When I just treat all of the data as equivalent and throw it in the same bucket and fit a model. Okay. So perhaps somewhat surprisingly, the results here are much worse when we have blocking. And in particular, when the OT data is small, right, we tend to do worse. And so maybe I've given a hint here by putting a question mark next to the blocking is bad conclusion because it's sort of counterintuitive in a way, but I'll try to explain why in a minute. Okay, but let's just take it as a given for now, right? We don't want to add factors associated with test phase because that'll maybe bias our results. Okay, so just to summarize, here's just the box and whisker plot of the root mean squared error by method, right? And the good thing is that integrating information is doing better than relying only on OT data, right? So all of these methods are doing better, and it's just a more of a matter of degree. Okay, so that's example one. Now I'll move to example two, which is just example one, except I'm going to add biases to modeling in sim and DT, right? So I just took a normal distribution and a normally distributed random variable and just added it to the intercept for modeling in sim and for DT. So we see that modeling in sim is more biased than DT, which is a little less biased, but still biased relative to OT, this is the true intercept from the operational model. Okay, so we're just going to kind of see what the effect of the biases are on the conclusions that we just reached. Okay, the first thing is Bayes, and really what we see here is now, the effect of the downweighting is maybe a little more ambiguous here, right? Like maybe we're doing a little better when we downweight more aggressively, which maybe you would expect, but the effect here isn't huge. We're not seeing like one method dominating the other. Okay. All right, but now if we look at blocking, right? So this is the plot I showed you before where no blocking looked much better. Now when I look at it, we see that the no blocking model is doing substantially worse than the model with blocking. And that sort of makes sense, right? Because we have biased data now, and like the MNS and DT data do not really quite represent what we should see in operations, right? But we're treating them as equivalent to what we got out of OT, right? And so as a result, we're getting biased models, like uniformly, and in a lot of cases, quite biased models, right? And so, the conclusion here is maybe more that blocking is good, right? And then finally, we can even take that non-blocking integrated model and compare it back to the original model with OT only data. And we see that we do quite a bit worse than that even, right? So the effect of integrating information has been mitigated by the fact that we didn't really use the right model to do it. Okay. And so we put all this stuff together, right? We see that the original three methods are doing quite well, and quite a bit better than the frequentist method, right? We're still learning things by integrating information, even from biased models, except in the case where we didn't, provide the right factors to kind of account for the differences between the data collections. Okay. And then, so integrated testing is, sorry, I'm just checking time. Integrated testing is helpful, but we have to have some care in how we do it. Okay, the point of this slide is really just that if we go to larger OT, the effect is somewhat smaller. We're only doing a little bit better, maybe than the OT only analysis, right? But the trends still basically hold, right? We're still in trouble here by virtue of using the data in the incorrect way. Okay, so just to wrap up, I think the only thing, I'm a little low on time and I want to make sure I have a bit of time at the end. So the only thing I want to mention here is maybe that it's worth mentioning that that we could only really integrate information because we're assuming that we had the information we needed to integrate it from the previous test phases, right? So we knew the factors under which the DT data was collected, let's say, for example. If we didn't have that, we wouldn't really have a hope of integrating it properly. Okay, so that's just maybe something from a practical perspective to mention. Where do we want to go from here? So we have this DoD-ish data generation capability, right? So we kind of want to experiment with different places in this consideration space that I mentioned. We want to use it a bit more to look at design of experiments. Like everything I showed you today was with optimal design at each phase. So it would be interesting to maybe look at a more sequential design, that kind of thing. And really kind of like longer term, where we would love to go is you can imagine, I mentioned that, right, different places in that consideration space might have different, might need different analysis approaches. And so you might imagine a decision tree for an analyst, right, that kind of walks them through, okay, well, what does my program look like? And maybe what is the right way to approach it? And what I showed you today, you could, I limited OT. We had other data that described the system, and the factors were changing in between the different test phases. So maybe we would land over here, right? But different programs will kind of wind up in different spaces in this decision tree, with the caveat that this is highly notional and is something I mostly just made up. Okay, so don't treat this as like Virginia Tech's take on this. Okay, so with that, I'm being told I have 2 minutes left for questions.